Okay, sorry, I added some noise and okay. So for example, um, you should enroll and do the courses, because if you don't enroll, you don't learn. That's the most important thing you have to do. By the ninth month of the first year, you should be in a position to write first two chapters of your thesis. An introduction, because you have chosen the topic, you know what the introduction should be like. And also as a PhD student, you have to keep writing. The more you write, the better you would be. And because you get feedback from your advisors and colleagues and senior students and so on. So you should exploit these opportunities. You should write introduction starting around ninth month or just before the end of the first year. And also you have to do a comprehensive literature survey. And this literature survey, you should write it up, not just reading. And you should be able to aim to submit to a reputable venue in the next 12, from the beginning by the 14th month, you should be in a good position to submit to a top class computing service. For example, ACM computing service articles, that style is very good to emulate. First thing is, when you write a survey, it's not just, Mr. A did this, Mr. B did this, Mr. C did that. That's not a proper review. A proper review is you introduce the topic and you introduce the what are the issues in the topic, and you do some categorization. And within each category, you should say what other people have contributed. This is some kind of almost like a book, but not quite a book, because it is not a general introduction, but sufficient introduction followed by concrete contributions of each individual. And then you also need to have some remarks, whether you believe, concrete way that these results are quite good, or what is lacking in those things. So important thing is, you really need to read some good computing survey articles and see how they framed and how they're written, and that's what you should be literally coupling the structure and so on. But remember that even though you have done these two, in the final submission of your thesis, you would be extensively revising these introductory chapters, including the survey. Okay, so again, coming back to topic selection, it is the hardest of all. PhD doing is trivial once you know the topic and once you know the problem you're trying to solve. And the reasons is, it is insufficient background from a student point of view. They don't have enough knowledge. And also conflicting goals. So, you might be interested in some other thing, some theoretical problem, but you think, if I work on that, I might not have a future because no company will hire me. There aren't many academic jobs, all these. And also sometimes you want to do a topic, but you also fear whether you are competent to work on it, because some theoretical questions are very hard because there are so many open problems. Whether P equal to NP, this is an open problem, and I don't think it would be ever solved in our lives. And if one of you try to solve that problem, you need to really think, whether you have the ability to do it. And this is where competence comes. And the second is it really worthwhile for you to do it? But if you solve it, you're going to win a Turing Award. There's no doubt about that. And you will have most prestigious professorship anywhere in the world that you like. But the odds are very, very low. And that's where you have to be very reasonable and rational not to choose. One of my PhD students chose a problem that Tarjan, if you know Tarjan, he is a very famous person from Princeton who worked on many fundamental data structures. And he wrote one of the open problems. Is there a linear algorithm to find closure algorithms? That is, if you have a graph, able to find all possible paths in a linear complexity. And my students spent 2 years, and every time we used to have an algorithm, and we used to find a slight loophole in that algorithm. So So he never solved that problem. In the process, he did other kind of contributions in trying to do, I had building some auxiliary data structures, and then we were able to do some transitive closure problems. So you have to be very careful how you select your thesis topic or thesis problem. Some of the better, reliable, safe approaches join the existing large projects. It's one of the professors have a big project running, several years, and he's continuously, producing completed PhDs. Then you just go in that group and then do it. But the problem with that is you may not be the topic that you really like it, and probably you may not be so excited that your contribution is rather limited because it's not completely your own original, but it is a safe way of doing it. The second one is instead of a project, you could join an established research group, a professor with, let's say, 5 or 6 PhD students, and then the students are pretty happy and they're very productive. Then, yeah, and you go and talk to that research professor and then see whether she or he has an interesting problem that you may be able to contribute to. That's another safe way of doing. Sorry, a lot of spelling mistakes. Join the person that you think can work with and communicate. So this is an important part to do as well. There are some people, they are very, very good, but they have no time for you. Then you will suffer, doing PhD under those individuals who are so busy traveling all the time, never in the office. So that would be very frustrating for a PhD student. Choose an advisor who is known to do well and well respected. So this is probably the best person to choose in my view. And again, these days it's so easy to find the best performing advisors based on their publications, where they're publishing. If they're publishing like IEEE or ACM, or in the case of AI, ICML, AAAI, ICHKAI, European AI Conference, and Machine Learning Journal, AI journals, and CKDE, say ICDM, and so on. These are the top places. If you get publications, any of these things, you're already an achiever. And remember, quality is better than quantity. You need to see where they're publishing and how the citations are. And some students have a very clear direction and they have a very clear problem they want to solve. And you should not worry anything. Just choose the problem and find a professor who is willing to back you on that problem, and just sit down and do the research. Okay, sometimes you need huge data sets. You need it for your thesis. Not only just using the topic and everything is fine, but if you don't have access to the data sets and if you don't have resources, then you are committing a big mistake. So ensure you have access to the data. All privacy and ethical issues are cleared, especially in Western world. Sometimes a PhD thesis cannot continue until you have. I had PhD students who worked on medical related area, and it's so hard to get the medical data. The professors in the medicine are willing to give us, but the problem is we have to go through ethics clearance, and that would take months. And sometimes some of these people who are the custodians of data, they don't want to, they promise you they would give you, but they won't act. They would drag forever. Sometimes takes months to a year. So that can eat away precious time of your PhD, and you're not doing anything every day. You go and read something or watch some websites or play computer games or whatever it is. So you're basically killing your precious PhD time, and you lose motivations and so on. Make sure you have computational resources as well. Just having data sets and so on. If you can't run big, sometimes you need big computational resources. For example, when we're doing an MRI for brain, we needed a huge computing because these MRI images with the deep neural nets, they are killers of power, and they are the greenhouse monsters. They create a lot of greenhouse effect. So you need to make sure that these are there. And if you need to collect data yourself, this is even more painful. Again, requires ethical clearance. Like, for example, even if they're nothing to do with medicine, like even if you want to collect, like I remember one of my colleagues was trying to collect data, how people are using smartphones. And because that involves human beings, they have to go to ethical clearance. Uh, um, and very time consuming and sometimes can take years to get these clearance. And then after that, collecting the data itself painful. If it is a wet lab related data collection, the pain can be even more severe as experiments may not work, results are not positive or not as expected and you hoped. And unfortunately, today, negative results, in my view, are as important as positive results, but it's very, very hard to publish negative results. Nobody's interested in negative results. Suppose if you say taking this medication doesn't help you cure this disease, it's very important, but nobody cares for that because they wanted, tell me the medicine that cures the disease. I don't care whether this medicine cures or not. So the same thing applies in all fields. So negative results, although they're very important, unfortunately, there is no places where you can publish unless this particular one popularly believed to be true and you prove it wrong, then you get a good name. So quality and quantity of data, this is a big problem. You can always measure quantity, but quality is very difficult to assess. Uh, and not only that, when you collect a lot of data, you need annotations. So for example, let's say I have access to 10,000 MRI images, but they are useless to me unless that each image is annotated. Annotated means you need an expert to annotate these images. Each image annotation might take half a day. How do get quality data of annotating these things? Well, I went through all of these problems when we're doing brain imaging. Okay. So need to know, okay, if you're going to work in data analysis, you have to be very good at statistics. I know a lot of people think they know statistics because they can run a couple of tools to do some kind of a validation, hypothesis validation, and so on. But I think it's nothing like really understanding basic fundamentals of statistics, and you need to really understand a hypothesis validation. You know how to compute p-values, and you need to understand the margins, and you need to know the power ratios, and so on. I generally advocate anybody working in machine learning and data mining, they have to be very, very good in statistics. So you need to learn a standard, undergraduate level statistics. Definitely, you need to know. Even if you need to know time series and so on, if you're going to work in sequences and so on. So my sincere advice is you have to do courses in probability and statistics. And why I said probability is much more theoretical and foundational subject, which helps you understanding statistics much more naturally. Just to let you know that my daughter, she is a medical person, um, and she was very good at maths, but unfortunately, she couldn't make use of her mathematical skills by staying in mathematics, but she went and did medicine, and then she became a kidney specialist. Then she did PhD at Cambridge, and then went to Stanford. And now she's doing a lot of machine learning work in medical area, especially in fundamental immune system, and she has to learn a lot of statistics. And I found she was so amazing in her statistics because in her high school, she did quite a substantial part of statistics. And somehow it became natural to her. Statistics she understands better than some of the undergrad statistics students. That's what I found. I think basically in it she is very good, but then whatever she learned, she didn't forget. And that's the basic dictum that, whatever you learn, don't forget it. Um, So need to know what quality data you have, know how to choose sample size. All of these are some of the statistics related one, and I understand this is kind of covered in your subjects. But remember, you really need to try some maths you should do by yourself and learn. You don't need huge number, even a table of 20, and do the hypothesis, validation, various tests will be there. And if you can do all by hand and understand why you have to do it, what is its significance, that would be very important. Um, and you have to be aware, sometimes certain you won't be able to get data sets easily. For example, if there's a rare medical disease and you can't get so many data samples. Again, just to give you an example, when my daughter was working on I think she was actually looking at schizophrenia, and then they had access to 6 human brains, and then they slice those human brains, and then they actually look at the structure in the brain, and usually they use some kind of an agent, and then that agent shows some kind of coloration in the slides, and from that they infer whether there are any new kind of cells created and so on. And I said, how can you do research with 6 samples? And she got so angry and told me, Dad, these are 6 human brains. What do you expect? So sometimes it is impossible to get large data sets. And another classic example is ovarian cancer. Ovarian cancer is one of the most horrible cancers for female, and they have to be diagnosed early. And then these uh, ovarians has to be removed from her to save her life, and she can never have children, but she can have normal life. But unfortunately, that has to be removed to save them, and it's very hard to detect ovarian cancers. Um, but that tissue is needed. We can get plenty of tissue because it's not a uncommon disease, because most of them unfortunately don't survive, and many of them are willing to donate their tissues while they are alive, because they will be removed most cases, or even after they passed away they would remove them and they donate. But in order to understand, we also need healthy tissue of ovarian. No person can give healthy ovarian because this is part of your body. You can't give it. Which female will donate ovarian tissues, even if she doesn't want to have children? This is nonsense to expect donation of an ovarian cells, healthy one. Usually, they end up those who die unfortunately in an accident or other causes. Then the family has to give permission to those tissues, and therefore we will not have enough data sets of a healthy ovarian tissue. So these are some of the practical issues that you have to realize when you embark into any of these topics, because these days most of the research can be done by computer scientists using machine learning algorithms better than any medical or a biologist can do. But of course, you have to work with them, but you are a real powerful person to do this kind of work. When I was at Melbourne Uni 20 years ago, you talk to any medical professors, they have no time for us. Now it is opposite. We have no time for them because they need us all the time. Many of them come and knock my door to work with us. Be aware of data collection issues, quality of data, annotation of data, and severely these things can impact progress and can be very frustrating to say the least. So these are the things that you have to do. So if the thesis involving coding and data generation, writing programs these days become so easy. Yeah, the interesting thing that I find in computer science, you would expect every student should be able to program. That's not the case. Some students are extremely bright. They can come up with very nice algorithms, but they can't code. And I have seen students who doesn't understand anything, but you tell this guy, write a C compiler, the guy writes a C compiler, comes back within a week. I have seen such amazing variation in those student capabilities. Some can code well, they don't make any mistakes. Some students code and it never works. Every time it only works on one example. And if when you ask them, can you try something else with the code, they have to go and rewrite the whole code. They don't plan how to write the code. So the best thing now is the most important thing is you have to learn software. Anything you produce has to be reusable. You are reusing, or be able to give it to someone else in the future, or next PhD student, or next, or you go and become an academic and you want to use it. So you need to uh, you know follow principles of software engineering, how to preserve these programs, how to annotate them, how to comment them, how to do the version control, and write general purpose one. You don't write one version for each one. For example, you might say, oh, I needed to do some statistical analysis, so there's one code for it. No, I need to receiver operation control curve, then another code for it. You don't want to do that. You want to package as much as possible all in one thing and then use appropriate flags to do it, which means you have to write a good quality software and so on. So, like, for example, I had a student who did some work, and then I tell him, oh, do tenfold cross validation. He goes and rewrites part of the code. When I tell him, can you do, not this one, I want some other algorithm, and then he has to go and reproduce another code. So that takes too much time and prone to errors. And you make sure that if you use some good version control, backups and all of them becomes implicit for you. And also be aware that the code that runs flawless today doesn't work tomorrow. Strangely, the software also has a property of rusting. Proper software does rust. So the reason is that you have a new version of operating system, and it thrown away all your environments that you set up in Unix or whatever it is. They're all disappeared, or somebody accidentally removed some initialization code, or .chrc or .hrc or .login, whatever those things have modified and so on, and therefore it doesn't work anymore. So you need to be very careful and make sure that you don't waste time in doing that. You need to you need an amazing discipline of documenting properly code, even more carefully documenting the data. Sometimes you can read the code and try to understand what you have done even after a year, assuming you had sufficient comments. For the data, if you don't comment anything, how it is collected, what the parameters you have chosen, there is no way of looking at the data and try to remember it. So data has to be documented meticulously, under what conditions you collected the data, what are the unreliable parts of it, and so on, who collected it, what time, everything has to be documented. And it's so easy to forget, what these things were after some time, and therefore you have to do that. Once again, the rule is that all these data sets that you have to be preserved for 9 years. That's the new rule. For every PhD student, data should be kept. For example, let's say somebody challenges you, all your results are wrong. Then could be a situation where your PhD will be nullified. You won't deserve to have a PhD. Then you will be challenged to reproduce the results. Therefore, you have to go back to your programs and your data. For example, at Melbourne University, thesis and all data sets have to be put in a permanent repository, and they will keep it for 9 years, minimum 9 years. In fact, they keep it forever. So the reason is the data will be useful. Second is one day somebody might challenge your findings, and there may be some questions on the ethics, whether you followed proper ethics and so on. So you need to preserve your data more carefully. And this is the next thing is never ever modify original data. Sometimes you collect the data and this is untouchable. Once you deposited and written all the documentaries documenting what this data about it, under what conditions you collected, and who supplied money, and who these what kind of age groups you collected, what kind of confidentiality maintained, all of these things well documented, age groups, and all of those things. And if you need to modify some reason in this data set, so for example, let's say you collected the whole data, and you needed to ignore some columns or ignore some age brackets or whatever it is. Let's say, for example, you're not interested data sets that belong to people who are above 90 years of age, for example. You don't go and throw away from your original data. You leave it. Maybe somebody else needs it later. So you produce a new version, and then you need to comment exactly the same thing. The sources, which original data came from, what changes you made, what columns were ignored, what errors you fixed. For example, if you believe some data sets wrongly recorded and you want to change it, you change in the new one, but never touch the old one, and then document it. And sometimes you have to produce synthetic data as well. Synthetic data will be very useful. Again, you have to use exactly the same rules as the original data, how the synthetic data was produced, what programs used, what assumptions you made, how the model was generated. You need to document all those issues. Okay, while collecting real data, one can start experimenting with synthetic data. This is the most important part. Sometimes people tend to say, oh, I will worry about analysis once I get my real data. I think that's a waste of time. And you should, while you're collecting the real data, you should start experimenting synthetic data that you produce. And synthetic data could be huge time saving. First thing is synthetic data could be produced with a large amount. So for example, let's say I'm doing some kind of a regression analysis. I can use any damn mathematical function and generate huge amounts of code and see whether my new algorithm that is trying to predict regression algorithm, can it actually do the nonlinear functions or something, erratically behaving function? Can it do it? Or you produce the synthetic data and then you corrupt it with a lot of noise and see whether my algorithm is tolerant to these kind of synthetic errors. And these synthetic errors that you introduce in your synthetic data will be very controlled. You could say, well, the noise I introduced is Poisson distribution, or it is a Gaussian distribution, or it's some kind of some noise that you collected, some speaker or something like that. So this is a good way of doing very good quality work with synthetic data as well. Many times synthetic data can be very close to real data that allows you to produce programs very quickly, these analysis programs very quickly, and they can also be validated in the future. For example, let's say you run your real data set and the results look very ugly. Then you wonder whether the data is the cause of the problem or the program itself. Then you go back and run on your synthetic data and you know what the real results are. And if your program shows good results, then it's clear the program is not doing funny, but something wrong with the real data. And then you try to investigate whether collected data was reasonable. Know the best tools and do not invent new tools. There's so many machine learning algorithms that are there. Try not to produce new one. You're going to make mistakes. For example, one of my PhD students went and spent nearly 6 months building database repository, for making version control, and also wrote a special program to, it's almost like make program for those who know Unix. It's a program that takes all the programs that are related together and run them and finally produce the final program. All these libraries, it brings them. 1 second, please. So this is, so he wasted 6 months writing these tools, and they are not very useful, and many times they're inferior. But my student is one of those gifted programmers, and finally what happened is that 3 or 4 years, then he became an academic in our department. About 4 years later, one Stanford professor from agriculture department came and he visited specifically my student because he used his tool to run his programs, and I was so impressed that he had an impact of his tool. Okay, so in order to progress your thesis well, I think the most important thing is how you interact with your advisor. And this might cause some inconvenience for the advisors, but I tell you, it is you as a student, it's important that you realize it is important for your future. Okay, so you need to insist weekly meeting, at least 1 hour long meeting, one to one. It is important. Uh, the student should always have something concrete to present or discuss in every meeting. You're not just going to, sir, can I see you? And then you say, sir, I want to go on a holiday. That's not the meeting I'm thinking. I'm thinking a research meeting every time. Okay. For example, if the student wants to discuss a paper or recent findings, the student should produce about 10 slides. Use your PowerPoints, whatever fancy stuff you have, 10 slides of the material and present to the advisor, and then start discussing the issues. First you present, and sometimes your professor might stop you on the second slide. Sometimes both of you have to be patient, because if it's a real concern, you have to address issues immediately. If they're not serious, you should say, hold on, sir, let me finish the rest of the thing, and then we'll come back to that. Okay, and I think that's an important communication to staff to have. And it's even better if you send those slides one day ahead, at least, to your advisor, who will be looking those slides in the night or early morning before the meeting starts, and that would be ideal. The meeting should be highly focused. You should have a very clear direction why you're meeting, and you need to be driven by that. And have a clear action points. After the meeting, you and your advisor would be discussing. You should write some action points and immediately record them, and then you have to email to each other. And the next meeting, you should look at those recorded action points, and then you should tell what has been done and what was the hurdle, and you have to do that. Every student should present 1 hour seminar every 6 months to the department as a whole, while making substantial presentations within the research team every 2 months. And this is a good practice, because when you do present, first thing is you learn how to present, from the voice point of view and the timing and so on. And you also learn how to structure your talk. And because when you give the presentation, can I continue?
Yes, sir, you can continue, sir.
Okay. When you present a 6 month presentation to the department, you have a different style of presentation, because not everyone work in the same area. You always have to do some introductory slides and then go on to the problem that you're looking at. And then you try to, sometimes your research could be quite intricate, but may not be the people may not be very interested to know all the intricate details, but you try to give highlight of your research and why they are important for them. Okay, this is a good way of calibrating your progress as well. When you give 2 months to your own group, you have to give introductory material. Maybe in the very first presentation you do, but afterwards you don't. You go straight into technical issues, or maybe slightly remind a little bit of the background, and then you do that. So when this comes, sometimes somebody who not necessarily working in the same field raises some interesting questions to you, which you probably miss with. And that can immensely help you to improve your presentation, improve your research, and so on. That's why it is important to have public forum presentations, not just the advisor. Now, these days, the AI tools basically cut shorting PhD time. In my view, when I did my PhD, maybe out of 3 years of me a PhD, maybe 2 years of PhD is just writing code and mundane type of code and trying to verify day and night. Sometimes you used to work until 2 a.m. until the code works because the machines were very slow. You wait for the other person to finish and so on. But these days, with the AI tools and the amount of money you have, um, and the amount of money you have, sorry, the amount of machines and AI tools you have, you can actually aggressively progress your PhD and make more substantial work on this. Um, so just to give you an idea, well, let's say you're working. Oh, sorry, I think. Excuse me, can I take this call? She is one of my mother's assistant. I think she lost. Give me 2 seconds, maybe 5 minutes break. Hello, hello. Check on. Check. Ah.